Here's the notebook where I'll show you how you can actually apply XLM-R to an application. The example task that we're going to be using is called natural language inferencing. And NLI is not my favorite task because it's really more of a benchmarking task than a real-world application. It'd be fun to come back sometime maybe and do like the toxic comments detector or something like that. But NLI happens to have a great data set for experimenting with this cross-lingual transfer concept. So that's why we're doing NLI. NLI is a sentence pair task, meaning we've got two sentences that we're going to feed into the model, and we're going to perform a classification task on those two. And it has to do with the relationship between the two sentences. So you could call them sentence 1 and 2, but they use the term premise and hypothesis, so we'll stick with that. So here's some examples. They can either be entailment, contradiction, or neutral. So these statements are taken from image captions. So it can help a little bit to kind of think of it in that context, to sort of imagine an image that this text could be describing. So the first sentence says, "The man inspects his uniform." The second says, "The man is sleeping." So here the verb is inspects, and here it's sleeping. You can't be doing both of those things at once, right? So that is a logical contradiction. All right, an older and younger man smiling. Two men are smiling and laughing at the cats. Okay, does the first sentence say anything that implies that they're laughing or that they're looking at cats? No. Is there anything that, about laughing or looking at cats that doesn't fit with the first one? And so no, it's possible that both of these sentences could be describing the same image, really. So that's neutral. And then finally, an entailment example, a soccer game with multiple males playing. Some men are playing a sport. All right, so that almost sounds neutral in that they're kind of, they sound like, yeah, those are exactly the same sentence. But I think you and I are kind of applying our own human logic to that to figure that out. Because really it says multiple males are playing, and it mentions a soccer game. But we know that soccer is a sport, and we can kind of tell from the sentence that it's implying that the males are playing soccer, which we know is a sport. So this is a logical conclusion that you could make from the first sentence. So pretty challenging problem, right? And that's why it's interesting. I think it's relatively easy to create these examples basically for the data set, and clearly they require a lot of sophisticated reasoning in order to correctly label. So it's a good task for helping us differentiate these really powerful transformer models that are already really good at NLP. There are two data sets that we'll be working with here, and there's sort of an unfortunate detail with the naming. The first one is called MNLI, or multi-NLI, except that in this context, multi does not mean multilingual. So it actually means multi-genre. And the reason for that is that the original NLI data set is the Stanford NLI data set, and that's the one that is taken from image captions. So the multi-genre NLI data set takes examples from different genres, fiction, letters, telephone. So I'll try to refer to that one, specifically as like English MNLI, because it's really just all English. It's a huge English natural language inferencing data set. And then the second data set is called XNLI. And what they did for this is they took a tiny subset of MNLI, 7,500 examples total, and they translated them, with human translators into 14 other languages besides English. So it's a total of 15 languages if you include English. And then here's kind of the table of all the languages that they've got. A lot of common ones. Swahili and Urdu are probably the two least common. Urdu, I've learned, is the language in Pakistan. It doesn't really include a training set, right? It just includes what they call a development set, 2,500 samples that are there for you to sort of test your model against as you're developing it, and then an official test set of 5,000 samples that you actually kind of run, get your benchmark score from. Yeah, and then a guy named Sam Bowman was at NYU was behind both of these data sets. So pretty cool contribution to the NLP community. Most of this notebook is pretty standard stuff, but I'll try to kind of skim through it and point out the highlights, the things that are different. So MNLI and XNLI, I use TensorFlow datasets, that library, to download MNLI, even though we're using PyTorch. It's just a nice library for accessing datasets like that. So again, it's large. It's got 392,000 training samples. So running this, you might want to take a smaller sample in order to run in a reasonable amount of time. If you take the full set, it takes about an hour and a half per training epoch. MNLI can grab 3 random samples. The examples are pretty straightforward. They just have a premise, hypothesis, and label field. So we can print each of those with a wrapper to fit it to 80 characters wide. And you can see in MNLI, since this is the multi-genre NLI data set, there's kind of some more complex examples here. All right, and then XNLI. So the data structure for XNLI is a little funky. They've got the premise and the hypothesis, and then underneath those, for the premise, they've got the 15 different translations. So, each of these are a string, but it's all the Unicode characters, so that's why it looks so funky. And then the hypothesis, they do it a little differently for some reason. They have a separate list of languages and then a list of the translations. So not sure why they did the data structure different, but it's all right. It works. Yeah, so there's 15 languages in there, and they're identified by their character code and the index in XNLI. So we'll be running this for Arabic, but you can basically change these 2 values and run it for any of those 15 languages. So we can check out a few examples here for Arabic. So a little more complicated this time, hypothesis and then translation, and then select the right language index. But there we go. We got some NLI examples in Arabic, and I have no idea what those say. Makes it fun. All right, some helper functions here. Let's collapse that guy. Yep. All right, so tokenizing. All right, so we're using XLM Roberta, and they've published both a base version that matches the scale of BERT base, and then a large version that matches the scale of BERT large. And then they've also published some large ones that have been fine-tuned on named entity recognition, if you're interested in that. So XLM Roberta does have a different tokenizer. So instead of the BERT tokenizer, we're using XLM Roberta tokenizer. Pretty simple change. Like the Hugging Face Transformers library makes this pretty easy for us. Yeah, here's another example of the kind of what the tokenization looks like. We kind of looked at that in the vocab notebook already. And yeah, I always have to, a step in all my notebooks, it seems, is to go through and tokenize all of the examples and then just measure their lengths. So don't do any padding or truncation, just measure the lengths. And then, look at the min and max and median lengths and plot the distribution of lengths. So this I like to see. They're nice and short. It looks like if we pick 128 as our sequence length, that almost everything should fit in that. And we can kind of confirm that, do a little math. Yeah, so there's less than 1% of the training samples are longer than 128 tokens. And the classes appear to be almost perfectly balanced. So that's nice. It means that when we do validation, we don't need to, we can just use flat accuracy. We don't have to worry about class imbalance. All right. So yeah, to do the actual tokenizing, I use the encode plus function. And if this were document classification, you would just put in one input text. But here, since it's a text pair operation, we've got both of them, premise and hypothesis. And we're going to pad everything out to our max length of 128, as well as truncate down to 128 for any that are too long. And we will have encode plus turn everything into PyTorch tensors for us. And then something interesting is encode plus does not return segment IDs for XLM-R. So I'm guessing that means that XLM-Roberta does not require an explicit segment ID mask like BERT does. All right, so we've tokenized, encoded all 392,000. Do a training and validation split so that we can use the validation split to, in between epochs, measure the validation accuracy, make sure that it's improving, and make sure that the validation loss is going down. If the validation loss goes up, that means we've overfit. All right, yeah, then you use data loaders. It's a PyTorch class. It basically handles the batching for us. So for training, you want to randomly select your batches. So we use a random sampler and specify a batch size, and then this PyTorch class will kind of handle breaking that up into batches for us. Validation data loader can use sequential sampling. Doesn't need to be random since we're just evaluating, not training. And then, yeah, we're going to fine-tune XLM-R on English, the English MNLI data set. So this is our cross-lingual transfer here. We're gonna train it just on English examples, and then we're going to see how well it does on Arabic test examples without doing any other fine-tuning with any Arabic samples. So again, we're using a different model type here. So there's a different class, XLM-Roberta for sequence classification instead of BERT for sequence classification. 3 labels since we're doing NLI. Connect to the GPU, definitely want a GPU. I did spring for Colab Pro recently. In this notebook in particular, I mentioned it takes like an hour and a half to train an epoch on the full training set. I wanted to train the full training set for you guys, so Colab Pro seems to help with eliminating disconnect due to timeout. And they also apparently will give you higher end GPUs. I did not know that they had V100s for Colab. The best I've seen with the free version of Colab is P100s. So that's pretty cool. All right, and then the learning rate. This is an important detail. Nick was the one who actually initially got this code working. And something I didn't catch at first, but he told me later, was that the learning rate seemed to be finicky. He had trouble at first with kind of these are like the default choices or the recommended choices for BERT. And this is the learning rate value he ended up going with for XLM-R. And I'm actually rerunning it right now to try one of the BERT ones for myself. Doing 3 epochs, doing linear learning rate decay. And then here's our training loop. So standard stuff. I don't think there's anything in here. Yeah, nothing fancy. It's the same model call as BERT. Once that's finished training on MNLI, we can evaluate it on XNLI for Arabic. So first we just have to tokenize the Arabic examples. So loop through the XNLI data set, extract the premise and hypothesis for our particular language, and encode them. Again, same padding and truncation. Yep, create data sets. Yeah, and the test set is also balanced. And then we can run prediction. So this is the same as our validation code. We're just kind of feeding in the examples and the attention masks. No segment IDs again though. And here is the table of results in the paper. It's kind of overwhelming, right? Because there's so many columns and rows to it. But what we're looking at is this row, XLM-R base, because we're using the base model, not the large model. And then we're looking at Arabic specifically. So this is their cross-lingual transfer score, 73.8. So we got pretty close to that. And then I did also try further fine-tuning it. You can take the validation examples from the Xnli dataset and fine-tune on those. So that gives you like 2,500 labeled Arabic training samples. And that improved the accuracy up to 74.2, which is said match the paper score. Well, it matches the score for Turkish. I think I was off by 1 there. So there you go. If you'd like a copy of that XLM-R notebook, it's available to purchase on my site. And if you pick that up, I've also included this second notebook that I created on this subject, where I took a monolingual Arabic model and tried it out to see how well it stacked up. So if you go to the Hugging Face website, you can search for community models. And I use this one here, BERT Large Arabic. Seems to be, actually BERT Base Arabic, excuse me. Seems to be pretty legit. It was trained on a very large data set, lots of downloads, so reasonably popular. And let's see, I took 2 approaches here with the monolingual model. The first was to try just training on the validation samples, the 2,500 Arabic validation samples from Xnli. So it's a small data set, but it is human labeled, human created. And with that, I got a score of 0.61, which I might be able to improve with maybe some hyperparameter tuning. So not terrible, but not nearly as good as what we were seeing with XLM-R. And then the second approach is to take the machine translated version of the English MNLI data set and fine tune on that. So it's a much larger data set, but the quality is presumably lower because it's been translated by a machine learning model and not a human. And that approach worked really well. We got a score of 73.3%, which is higher than the 71.6 that we got with XLM-R. And of course, we might be able to do even better than that by further fine-tuning it on those validation examples from Xnli. To show those kind of in comparison, put together a little table. So using the monolingual model and only training it on that small number of validation examples gave us the worst score. And then the next best was XLM-R in my notebook, which did not score as high as the result reported in the paper. So some further fine-tuning, hyperparameter selection kind of stuff to do there, I think. But then with the monolingual model, with machine translated examples, labeled examples, I was able to do almost as well as the paper result and better than what I was able to achieve easily with XLM-R. So that's pretty cool. I'd say, keep in mind, like, this was only possible because a good monolingual model existed for Arabic. I tried looking for one for Indonesian, and the only model I found was trained on what looked like a relatively small amount of text. So I was a little skeptical of that one. This also required that we had a large labeled data set in English, and then that data set had to be translated into Arabic. And I didn't do that translation. That was provided for us as part of the Xnli data set, which is nice. So if you wanted to apply this technique to different task, different application, you'd have to do that translation step yourself. So one more thing to figure out. Maybe a good topic for another video. Yeah, really interesting topic. was fun learning about, different languages and some of these problems that impact the different languages out there. So glad I had the opportunity to share this with you guys, and I hope you find the notebooks useful. Thanks.